Hello, everyone. My name is Karthik, and I'm a Senior Solutions Architect in AWS, focusing on Amazon.com as a customer. I have with me today Amin Kazironi. He heads up the machine learning and research team at Zappos.com, and we're here today to talk about how Zappos leverages AWS for near real-time search optimization and sizing recommendations. In today's agenda, we're going to talk about the ML data usage. We're going to talk about crowdsourcing your data warehouse, talking about the event ingestion, the real-time optimization platform, scalable APIs, and how we're going to take the research to the customer. In the vision today, if you look at it, we have events, and these are the events that engineers register when we have near real-time ingestion. We also have our machine learning platform where scientists build, register, and deploy our data sets. And we also have APIs where our customer-facing experience, where customers can interact with our machine learning platform. And the intent over here is everything should be hands-off. And what I mean by that is no human intervention or retraining or deployment of machine learning models that we already have in production. And finally, have real-time, dynamic, user-focused, and recommendations for our customers on the website. Now, let's take a 10,000 feet view of how the architecture actually looks like on AWS. On the left-hand side, we have our event ingestion platform, where we have our worker nodes on the top doing all the heavy lifting. And then we have managed services like Kinesis, Lambda, Redshift, and S3 that do all the event ingestion for us. And then we have the orchestrator that talks about, that also has its worker nodes. And we have DynamoDB used for our key value data store. We have SageMaker that's doing all the machine learning processing and data modeling and building. We also have Glue that is using the ETL or doing the ETL transactions for us. And we also have EMR for all the Hadoop or Spark workloads that we have on our orchestrator workloads. We also have near real-time ML API. Again, we have our worker nodes doing all the heavy lifting. We have SageMaker for doing the machine modeling or the real-time data modeling stuff. And we also have the endpoint client that is consuming all of these data sets. Now, I'm going to hand off to Amin to talk to you about how it actually works.
Hi, thanks Karthik for that introduction. Like Karthik said, my name's Amin Kazironi. I head up the machine learning research and platform teams at Zappos. And today we're here to talk about the machine learning platform and the various components that go into it, built on AWS, that allow us to power experiences like a near real-time personalized search experience, sizing recommendation algorithms, various recommendation widgets across the Zappos experience. The primary goal being keeping the customer happy and doing that using some of the managed services provided by AWS. So like Karthik pointed out, the core crux of the engine is a real-time event ingestion platform, followed by a automated DAG orchestrator, and finally a microservice-driven machine learning API that exposes the various models that we build out to the customers. The customer being our clients on which the website runs, and also internal facing clients to help with various operational optimizations. So the reason it's broken up into those three components is that at its core, machine learning requires data. And there are some fantastic managed services in AWS that allow us to leverage data when it's available. But a fundamental problem faced by various companies, Zappos included, is when you're trying to solve a problem with machine learning, you're very often faced with what is called the cold start issue, which is you may not have the data available. The event ingestion platform that we're about to jump into provides a framework that lets engineers that are building the experience for your customers register events based off their understanding of what the experience does. That event registration is done in a custom meta language designed by the Zappos machine learning team, which effectively results in automagic spin up of the AWS infrastructure required to capture that event in near real time coming in from the client. What that then feeds into is a data lake that allows us to build machine learning solutions on top of it. So let's jump into that for a second. The event ingestion platform has the internal name of Amethyst. Fun little thing we do on the data science team at Zappos is name all our services after semi-precious stones, because it's always enjoyable to make it extremely confusing to know what a service is called. Let's jump into the architecture a little bit. Right at the start of the infrastructure, we have a lightweight client library that is developed and maintained in Swift, Java, and JavaScript. The reason for this is that allows us to ingest events from our iOS app, our Android application, server-side applications, and the front-end website and mobile site. What that event ingestion platform, what that client-side library allows for is the registration of events. It handles the bundling of events, and it handles firing off those events over to the Amethyst APIs. The Amethyst API is effectively a collection of EC2 worker nodes running inside an autoscaling group, which allows it to scale up and down depending on volume and load given the time of year. The Amethyst API receives these events and then makes a decision as to whether the events need to be passed on to a worker or not. Between the Amethyst APIs and the worker, we have a Redis cluster that acts as a session cache. What happens here is events get registered into the Redis session cache along with a session ID. This allows the Amethyst worker to do any resolutions that require events spanning over a period of time. That is sessionization, or let's say you're trying to figure out a search page click-through from the search page to a product page, and you need to be aware of two events. That over time processing occurs by pinging this Redis cache. Any resolution, for example, IP address to geolocation, user agent to a breakdown of browser and device type, all happens in the Amethyst APIs itself because it is isolated to the event itself. An example of the type of resolution that can be managed is deduping. Deduping is proven to be tremendously valuable when it comes to keeping the size of the data lake managed. For example, a user agent is something that you would want present on every event that comes through, but that can turn out to be an extremely expensive piece of data to store for every touch point that a client may have. The deduper effectively allows you to hash a component of an event, which then results in a hash key. There's a dynamo table that you can look up for every deduped portion of an event. It checks if the hash key exists. If it does, it forwards on the hash key to the data lake. If it doesn't, it makes an entry in the dynamo table and an entry in whatever your managed data warehouse is for lookups against that hash key, and then registers that new user agent or collection of A/B tests or what screen resolution or any repeatable piece of information you can think of. Effectively, if the hash is smaller than the repeatable event component, it's cheaper to store the hash. From there, the events are put into Firehose. What Firehose allows us to do is stream the data to S3 and to Redshift. The benefit of this is that without any DevOps overhead, we're able to get this data in near real time, doing micro batch copy commands available in our Redshift database for analysis. In addition to this, like we'll see a little later, Amethyst also supports multi-destination, which means that at the API and worker level, we can have the event definition allow for clients to register additional destinations for the events to go to. For example, S3, Kinesis, additional Firehoses that could be streaming in Parquet, format into S3 that allows for a Glue metastore that you can run Athena on top of, and a variety of various data lake solutions that are available in AWS. And what this allows for is the democratization of your data across your corporation so that various orgs and teams within your corp can register to specific event types that are important to them, so you don't end up duplicating the data warehouse over and over again in its entirety, but you can compartmentalize it. From Firehose, the data ends up in S3. Unfortunately, we weren't able to use the direct Firehose to Redshift functionality available because we wanted the Redshift cluster to be in a private VPC with no internet gateway on it, and we wanted to put encrypted data in there. So like you can see in the architecture diagram, there's a KMS key available with a decryption lambda that is embedded in the Firehose itself, which is a cool feature Firehose provides. It allows you to do record level translations and operations on every event that is inside your firehose. We leverage that for encryption decryption. The encrypted data then is sitting in an S3 bucket that a Lambda that's running in the same VPC as the Redshift cluster will go and pull in and do copies regularly at regular intervals. This will pose some challenges in terms of Redshift connection limits. So I would advise to be cognizant of this and consider using external tables where necessary. So you're not doing constant loads into a Redshift cluster because it becomes difficult for then your groups of analysts that are querying it. But that's an optimization that varies from org to org. And I would encourage you to keep that in mind while implementing something similar. So let's talk a little bit about the multi-destination support. This was a feature and functionality that came later in the game in the Amethyst ecosystem. What this allows for is custom event matching logic, which effectively allows the workers or APIs in those collection of worker nodes, those two classes of worker nodes like we saw in the Amethyst architecture, to effectively look for specific occurrences in your event stream and then based off that custom logic, divert the events to various destinations. So this could be a Kinesis stream for real-time analytics or monitoring or anomaly detection. This could be more sensitive data being fed into an S3 bucket that you got Macy running on. This could be your data lake that's being put into S3 in Parquet format for Glue to run on, have a Glue metastore on for Athena, or it could be multiple fire hoses for specific events for other teams in your org that want smaller, lower footprint Redshift clusters. What's cool about this is the Amethyst workers are able to assume the role in the client's AWS account and then use AWS keys in their account to provide encrypted data in your own data storage solution across your organization. So this is proving to be tremendously valuable because what happens here is we are able to define the event at the engineer level, which means an engineer that's producing a new feature on the website goes in and just registers an event definition. What that results in is a layer that interfaces with various AWS APIs and then spins up the infrastructure needed to track that event, which is the fire hoses, updating the Amethyst API to be able to receive the new event. Within 30 to 40 minutes of a CI/CD environment, we have the deployment live and that event ready to be ingested live from the client without any engineering intervention. What this resulted in is after our initial set of events that were registered by the data science team for the machine learning algorithms that we wanted to train, we are seeing a multitude of new events being registered by our engineers, and the growth of the data lake is exponential. We're able to unlock new machine learning solutions. We're able to think of new problems that we want to tackle because there's fresh data coming in that we would not have even thought of capturing. So I think that is a spectacular outcome of that infrastructure, and it's really exciting to see engineers take this very proactive role in producing data for machine learning. What that then takes us to is Peridot. When you've got a large data lake, when you've got rich information, you are now in a position where you're training a lot of machine learning algorithms. When you're training a large number of machine learning algorithms, you realize that there is a logical maximum for the number of machine learning algorithms that can be kept in production by a team of machine learning scientists. Simply put, if you've got 5 machine learning scientists, they all build their first algorithm, and 5 algorithms go live. Once those are in production, you're not going to be able to build 5 more because there's some cost associated with maintaining those and keeping those live in a production state. That is when we realized that we had the opportunity to leverage various storage and compute resources in AWS and the API that is exposed by AWS to kind of automate that process a little bit, which led us to building Peridot, which is a DAG orchestrator. DAG is effectively a directed acyclic graph. High-level architecture is the users come in and register a DAG or a machine learning workflow in JSON format, which is a very consumable representation that a lot of people are familiar with. In fact, it's so commonplace that you may be familiar with it without knowing that it's called JSON. We have a contained Peridot VPC inside which we have the Peridot admin. What this does is it's aware of all the workflows that are registered and the cadence at which they need to run, or whatever triggers are required to make them run. Various triggers that you can think of for triggering a machine learning workflow could be a manual trigger, a cron tab that does it at some specific time windows, time lags. You could have CloudWatch events that are triggering a machine learning workflow off of some specific occurrence. And you could also have other workflows trigger fresh workflows, given that the output of one job could be the input of another. We then have a Lambda that's effectively a workflow launcher. The Lambda is in constant communication with the DynamoDB table that's effectively keeping track of each step of the workflow and its execution status and moving the orchestrator through the workflow. What's really efficient about this is that it allows the machine learning scientists to be constantly aware of where the progress that has been made in their workflow. It also allows the machine learning scientists to go in and look at detailed logs, which are available from every managed AWS service that allows you to understand exactly what went wrong or what's going right. Additionally, the client configurations and workflow configurations are also accessible to the Peridot admin. When I say client configuration, this is because we've reached a point where we want other teams and organizations within the company to be able to register workflows against Peridot and run their own jobs. What the client configuration allows us to do is allows you, as a client, which is an internal team, to register an AWS account with Peridot, and we use tags to handle permissions using IAM roles, which then allows us to leverage compute resources inside a client AWS account, which allows us to push findings, insights, and outputs to storage solutions inside a client's AWS account. This is the admin portion of the Peridot infrastructure. We then have the orchestrator here's an example of a workflow execution log. We're effectively looking at a collection of workflows for various machine learning algorithms with timestamps as to the last time they completed. And machine learning scientists are able to come in, look at the workflow executions, restart, retrain, or just let it do its thing. Over here, we have the Orchestrator Architecture. Basically, in the middle of the Orchestrator Architecture, we have the Peridot admin that's effectively keeping track of which workflow is running and where it's reached. We have various storage solutions like S3 and Amazon Redshift available for data acquisition, which is the first step in any machine learning workflow. We then have various compute resources like EMR, Glue, EC2 that are available for training and feature engineering. Effectively, feature engineering has turned into such an important part of the machine learning workflow that it can be extremely involved and compute intensive. So it's become critical to have infrastructure to support a variety of compute resources given the type of feature engineering that you're going to be doing. And finally, we have an assortment of deployment strategies available as well. We see listed over here Amazon S3, SageMaker, and Dynamo. Some of those may seem odd as the deployment location for a machine learning algorithm, but let me walk you through a few examples. When it comes to Dynamo, what we do here is deploy pre-computed machine learning solutions. That is, we train an algorithm and then we make batch predictions on anything we may need in a future state. This is proven to be tremendously valuable when it is a situation that has got predictions that are a manageable number, so you do not need to do it in real time. And two, you do not need real-time information to make the prediction. That is, historical data is enough to run your evaluation. So if those two tenets hold true, I would highly recommend pre-computing because it's always more expensive to make a live evaluation than it is to just serve a key value pair out of a DynamoDB instance. For when you can't make a pre-computed machine learning algorithm live, we have S3 and SageMaker available to us. SageMaker endpoints have proven to be tremendously useful. It's very simple to just have a small Python script that does your evaluation, expose that via a SageMaker endpoint. You can swap out your artifacts very efficiently by just updating a YAML file or using an API, which has proven to be very valuable when it comes to training these machine learning models out of band. Even if we're not leveraging SageMaker for the training and feature engineering pipelines, we're still able to leverage the SageMaker endpoints for the evaluation layer. When we use S3, it's something called PMML, which is a predictive model markup language. It is a standard that is developed for the representation of machine learning algorithms. It supports Spark, scikit-learn, R, Python, language agnostic, and a variety of machine learning libraries. You're able to export your models into PMML format in whatever language your machine learning scientists work in, and then load them up in whatever language your API developers work in, and then expose those machine learning APIs. So those are the three infrastructures in which we're able to deploy machine learning algorithms. What we're going to look at next is an example of one of these workflows and what they look like. So here we have a simple workflow that effectively spins up the resources needed, which is an EMR spin up and a Jasper unload step, which is effectively a data retrieval from our data warehouse that is known as Jasper. We then have a feature engineering layer followed by a training step, followed by a Dynamo deploy. This is an example of a pre-computed machine learning model. The feature engineering derives a complex set of features, which feeds into the training, which trains a new copy of the algorithm, does batch predictions, and pushes them into Dynamo. What's really cool about the Peridot orchestrator and infrastructure that we've developed is that it has an awareness of what it means to be a model. Effectively, a machine learning model is a snapshot in time given a certain set of data and a certain set of hyperparameters that were trained, which means every time you train these different machine learning models, they can have different accuracies, they can have different coverage depending on the hyperparameters and data sets that were used. Over here, you're able to see a history of all the models that were trained and actually do one-click deployments by hitting Make Live that knows the deployment state of that particular model type and can go ahead and update it, which then brings us to what is known as Opal. Again, very, very diligently following the theme of naming our services after semi-precious stones. Not precious stones, just semi-precious. Opal is our microservice API. It is effectively able to expose machine learning algorithms for any of the three deployment types that we spoke about in Peridot. Opal actually came first out of all these microservices. As you can imagine, the automation of the DevOps side always comes after you've proven value. So our microservice API came first. This is a fairly simple architecture. It's not very nuanced, but it's able to handle high throughputs of traffic. It's able to scale dynamically. And most importantly, machine learning is a compute-intensive thing to do even at the evaluation, especially at the evaluation stage, when you need to make real-time predictions while maintaining customer-facing SLAs. So the Opal microservice API has evolved over time to allow us to be able to continue to power complex experiences like search and sizing, which we'll get into in a second. So let's talk about the Opal API infrastructure. It's a fairly simple architecture made up of a collection of EC2 machines, which is our core compute resource running inside an auto-scaling group. The requests come in through Route 53 using location-based routing. There's microservices running in each region contained inside their own AWS accounts. Route 53 is running in an independent AWS account that just routes the traffic to the appropriate region given where the request is coming from. The request hits our load balancer, which then hits the microservice. The microservice is made up of a collection of EC2 instances running in an autoscaling group that can scale horizontally as traffic demands. It then calls back to either S3, a SageMaker endpoint, or Dynamo, wherever it's making the model prediction from. It is constantly aware of which model version of the model it's serving from, as there's a model UUID that is provided by Peridot upon deployment. Additionally, we have a Redis cache that's running in a Redis cluster that also provides a level of scaling as needed. The Redis cache has predictions in it, effectively predictions that have been made for certain keys or certain sets of data are cached in the Redis cluster so that we're not going back and trying to make the same prediction with the compute-intensive process over and over again. Dynamo itself has auto-scaling implemented in it, which allows for a third level of scaling in case of a sudden influx of traffic. An important thing to keep in mind is when you hot swap models, that is just invalidate your cache because a new version of a model is going live. A lesson that we learned is sometimes it's good to pre-scale your Dynamo tables so that you don't suddenly hit it with a large volume of traffic that it's not been used to. But the Dynamo autoscaling seems to handle that fine if you let it deal with it on its own. But, just to be safe. So this is the Opal architecture that effectively allows us to serve the PMML models by loading the PMML into S3, the SageMaker endpoints by proxying the SageMaker endpoints or directly exposing them, by routing the traffic there when needed, and the pre-computed models by exposing the DynamoDB tables. The cool thing about the Opal architecture is that the way the microservices are laid out is that they are logical partitions based off what type of model is being served, with a synthesizer microservice in front of it. What the synthesizer allows us to do is produce some very interesting features, which is various combinations of the assortment of machine learning algorithms that are present inside the ML ecosystem. So let's talk a little bit about the outcomes of this infrastructure. So some of the examples of features we're able to power on the website are real-time sizing predictions, autocomplete and search, facet navigation optimization, the actual search algorithm itself, and unique product recommendations cohesively throughout this Zappos experience. Let's talk about search a little bit. Search is a very complex feature to try and power in real time using machine learning because it's kind of the first line of defense in an e-commerce experience. When someone comes to a e-commerce website and types something in, if the first thing they see is not relevant or meaningful for them, you can lose the customer. If it is relevant and meaningful, that's when you can gain a customer. So using machine learning to power this kind of relevance and optimization is a logical next step, but it's important to be able to do this in a production environment. The Opal microservice allows us to power experiences like the one you're seeing right now, where the best for you sort, as we call it, is a completely different set of results than the relevant sort for the same search term, given who the customer is and the context within which they're searching. Now, right there in that sentence is why a microservice API exposing multiple machine learning models is critical. We need to understand who you are at that given point of time, and then we need to understand the facets that you've selected, and then we need to understand the search term that you provided, and then we need to figure out how outputs of all those machine learning models can be translated into something that makes sense to our search index to re-rank hundreds of thousands of products. A microservice API allows us to pull the machine learning outputs for each one of the individual models that are needed in parallel and then blend them together at real time so we're not pre-computing a tremendously large amount of information. This is what allows us to serve personalized search recommendations without the customer experiencing any loss of service in the SLAs or load times on the search results page. Another feature we can talk about is recommendations. Over here, you have a brand recommendation widget. It's a very simple widget. You see a collection of brands in them. The reason it says complete features at the top is that this is not a single machine learning model that says, oh, it's Amin, these are the brands he likes, but the widget needs 6 brands. I only know 3 brands, so we're just going to leave 3 slots empty. That's not a good experience. It's not satisfactory to the customer. So there's a principle we follow in the machine learning team called degrading gracefully. Effectively, if we have only 3 predictions for a mean, you provide those 3 predictions, and then if you don't have anything else, but you're aware of a mean's gender, you can provide the top trending brands for that gender. If you don't have anything else, if you're aware of a mean's location, you can provide top trending brands in that location. If you don't have that, you can provide just the trending brands in general. So what that does is it gives you the opportunity to power a machine learning experience rather than a machine learning algorithm. Lastly, we've got an example of sizing prediction. What the sizing prediction algorithm does is it effectively shows you your size in any shoe. The reason this is advantageous to Zappos is that sizing is a very complex problem when it comes to e-commerce and retail online. Customers are trying to constantly find a size that is comfortable and are always living in that fear of having to return something. So this is an interesting problem to solve because Zappos is always customer service first, which means shipping is free, returns is free, 365-day returns. So how do you deal with that without taking those value props away from the customer? If you make them start paying for returns, you're not really solving the problem as for the customer as much as you're just solving it for yourself, which is why the Zappos team leveraged this infrastructure to be able to learn the customer's sizes in each brand and each product and make real-time predictions. And we've actually seen tremendous decreases in our return rates since the deployment of this algorithm, which is a win for the customer and a win for the operational costs of the company. So that has been a preview of the various components of the machine learning architecture and infrastructure that we have at Zappos, and some of the components and features that we're able to power using that infrastructure. Thank you for listening, and I hope you enjoy that.